Hello guys, in this video I'm gonna continue the discussion about Bode plots. So last time we introduced what is meant by Bode plots, and we take some examples, like for example how to draw a Bode plot for a constant, or a simple zero like this one, or a ball like this one. Okay, and also introduced what does zero mean, what ball mean. Okay, so you can basically review that video if you like. In this video, I'm gonna introduce you two other examples based on what we discussed last time. But feel free, to watch this video. I'm gonna start from scratch again, but not so scratchy. So we're gonna introduce simple zero and the simple ball, and also what happens if you have exponent. I didn't explain the exponent before. Okay, in that case, the ball origin or zero origin, but I'm gonna explain it here. Okay, so let's go on. Number 4, simple. Let's start by the simple zero. Okay, h of omega, the transfer function. Okay, 1 plus j omega divided by omega c. This is the first time to see this omega c. Okay, I'm going to explain it, and you notice that I didn't put any exponent. The exponent basically is 1 here, but then once we finish that, we're going to see the exponent case. Okay, so we want to draw the Bode plots for that function, for the magnitude of that function. So the magnitude of h of omega equal to the magnitude of that 1 plus j omega divided by omega. Okay, so and this is the first example that we're gonna see the brilliance of basically the Bode plots, how they can approximate a very complex function into a very easy like plot or drawing. Okay, so to draw this function approximately, because Bode plots are approximate plots for the real like graph or the plot of the function. Okay, we're gonna divide the scale into two cases. The first case, if omega is much less than omega c. C here is not the C like capacitance. C is a subscript, means the cutoff. Omega c called cut off frequency. We're gonna see why is equal to cutoff frequency. Why? Okay, so the first case, omega is much. I'm sorry, not. Yeah, much less than omega c, or we can say omega divided by omega c is much less than 1. Omega much less than omega c, or omega over omega c is much less than 1. Okay, in that case, Bode, which is the one that invented that, he said that we can approximate the function, this function here, into 1. Because 1 plus something very small approximately equal to 1. And the magnitude of 1, of course, is big. So h of omega is equal to 1, or the magnitude of h of omega is equal to 1. So 20 log the magnitude of h of omega. Remember, we draw a logarithmic on a logarithmic scale, okay, as we discussed last time, which is different from the normal scale that we see in our like Cartesians, like axis x and y. Okay, I'm gonna explain it again in a minute. So it's equal to 20 log 1. Log 1 is 0. That will be equal to 20 multiplied by 0 is 0. Okay, that's the first case. So number 2. The opposite now. If omega divided by omega c is much larger than 1, what's going to happen? Now we're going to neglect the 1. So h, the magnitude of h of omega, equal to approximately J omega divided by omega c. We're gonna neglect the one now. Okay, that's equal to omega divided by omega c. Okay. Now let's have cases. Okay, so like points, so we can connect these points and and they get the graph. So omega equal to omega c. Before that, again, we draw or plot 20 log the magnitude. So 20 log h of omega equal to 20 log omega divided by omega c. Now let's both cases. First case, omega equal to omega c. That will be 20 log 1, 0. Omega equal to, remember, that's a logarithmic scale. So we want to go by multiplying tens. So 10 omega c. Last time, if you guys recall, when we put some values for omega, we put 1, 10, 100. So we multiply 10 each time. 10 multiplied by 1 is 10. 10 multiplied by 10 is 100, and so on. Okay? Here, the first value we assumed omega c. So everything else will be in terms of omega c. So 10 omega c, then 10 multiplied by 10 omega c, which is 100 omega c, and so on. Anyway, so 10, 20 log. Now omega over omega c is 10. Log 10 is 1. So 20 multiplied by 1 is 20. Omega equal 100 omega c. 20 log 100. That will be 40, because log 100 is 2. 2 multiplied by 20 is 4, and so on. Okay. Now let's draw that. So let's have our scale here, our x-axis basically. Which is the omega axis. Okay. And we're gonna put like some points to represent the scale x. So we're gonna put, for example, like 10 to the power of minus 1 omega, 10 to the power of minus 2 omega c, I'm sorry. Omega c, look, we multiply by 10 each time. 10 omega c, 100 omega c, 1000 omega c, 10,000 omega c, and so on. Okay. You see, this is logarithmic scale. The normal scale that we have, we add, like, for example, stopped by 0, we add 1 each time, for example. So each time we add 1. Each time we add 1. 1 plus 0 is 1, 1 plus 1 is 2, and so on. Here, we multiply by 10. Look, 1, we multiply by 10 is 10. We multiply again by 10, so 100, and so on. That's logarithmic scale. Okay. So, but the y-axis is normal one. The y-axis here is 0, and 20, 40, 60. So we add each time. Minus 20, minus 40, minus 60. Okay. And when we take 20 log something, the unit will be decibels. So that's 60 decibels, 40 decibels, 20 decibels, 0 decibels, and so on. Okay. Okay. So we know we have two cases. Let's now draw with like another color. We have two cases. When omega much less than omega c, okay, we know it will be h of 20 log h of omega is 0. Okay. So we're gonna put zeros. Actually, we're gonna put 0 even I'm sorry, until omega c. Okay, that's an approximation, by the way. We should only put 0 when omega is much less than omega c. Okay, but we're going to continue with the zeros until omega c. When omega equal to omega c, look, we have zero. That's why I continued until omega c, although we know that only zero when omega much less than omega c. Okay. Again, Bode plots is approximations. I'm going to show you where is exactly we approximate. Okay. We usually approximate around omega c. Okay. So that's drawn now. When omega equal to 10 omega c, we have 20. This is 10 omega c, and that's 20 decibels. Omega 100 omega c, we have 40. This is 100 omega c, and that we have 40. By the way, 1000 omega c, it will be 60. So now we can continue and draw, connect these dots together. Okay. So we have like a straight line, linear. Okay. And the slope here is 20 decibels per decade. What is decade? The decade is the distance between 2 points. That's called a decade. But only if the ratio between them is 10, multiplied by 10. That's a decade. How we can prove that is very easy. Look, here is 0, this is 20. So for one decade, we increase the 20. That's why it's 20 decibels per decade. Also, you can get this from here. Between at 10 omega c, it's 20. At 100 omega c, it's 40. So again, the difference is 20. So again, for a decade, we increase the 20. That's why it's 20 decibels. And that's basically, that's here, 20 log the magnitude of h of omega equal to 20 log magnitude of 1 plus j omega over omega c. But this is an approximation. That's the Bode plot. The actual plot will be something similar to that. See, guys, around omega c, we have some approximation, as I said. So it will be something like that. Okay. So you start by 0. Then at around a decade before omega c, you start to rise like that. And around another decade after omega c, you go back and continue straight line. These two red lines, this guy and that guy, called asymptotes. Asymptotes, yeah, because the actual curve follows them, but only on the extremes. Or, not only on the extremes, like 1 decade after omega c, 1 decade approximately again before omega c. And that's the brilliance of Bode plots. You can approximate such non-linear curve with linear curves. Okay. But in exam or in a course, you just need the red lines. Okay. Don't put this like purple ones that I just added. But I'm just showing you something close to the real one. Bode plot is approximation. Okay, but very strong ones. Okay, now what's going to happen if we have an exponent? Number 5. If we have exponent, if h of omega equal to 1 plus j omega divided by omega c to the power of n. Okay, any exponent where 3, 4, whatever. We just continue the same way. So 20 log magnitude of h of omega equal to log, okay, 1 plus, the magnitude of 1 plus j omega divided by omega c to the power of n. Okay. What's going to happen? You know that x log y to the power of n equal to nx log y. That's what we're going to do. We're going to multiply the 20 by the n. It will be 20 n log 1 plus j omega divided by omega c. Oh, that's exactly what we have before. But instead of 20, it will be 20n. Okay. So what's going to happen? The slope will be 20n, not just 20. Here is 20 multiplied by 1 because the exponent was 1. But in that case, we're going to have the same drawing, the same plot, but it will be 20n. We're gonna solve it, don't worry. Again, we have two cases. Number one, omega divided by omega c is much less than 1, or omega much less than omega c, that's the same. In that case, 20 log 1, it's 0, again 0. So before omega c, everything is 0. Number two, omega divided by omega c is much bigger than 1 this time. So that will be 20 log j omega 20n, I'm sorry, there is n here, over omega c, that's 20n log omega divided by omega c. Then we put cases as usual. So for example, omega equal to omega c, so that will be 0, because this will be log 1, log 1 is equal to 0. Omega equal to 10, omega c, this is 20, and log 10 is 1, so 20n. Omega equal to 100, omega c, that will be 40n. 40n. Okay. Again, if you want to draw it, be the same drawing, and let's do this quickly here. We don't need much points. Let's assume this is omega c, then omega c, 100 omega c, this is 1000 omega c. Okay. So, and that's our y-axis here. 20, 40, that's enough. Minus 20 here, no, it's 40. Decibel, of course. Okay. When omega, this is 0.1 omega, omega c. So when omega less than much, omega over omega c much less than 1, we have 0. And once we go to omega c, at omega c we also have 0. Then at 10 omega c we have 20, 20n. Yeah, so let's, yeah, that's very good here. So that's, so here we should write 20n, 40n, minus 20n, minus 40n. In a real example, you're going to know n and omega c, don't worry. You know? So you're going to have numbers here instead of 0.1 omega c. For example, omega c is equal to 10, for example. So this will be 1, this will be 10, 100, 1000, and so on. And the n is going to be known. Like, for example, n is equal to 2. So this will be minus 80, minus 40, 40, 80. Okay, so don't worry about that. So 10 omega c is 20n. 100 omega c is 40n, and this one, 80n, and so on. Okay, and the actual curve will be something like that, similar to that. So it's 0, approximately 1 decade before omega c, it's gonna rise up a curvy with a curvy shape. Then approximately 1 decade after omega c, it's continue straight line, approximately again. Okay. Now, final case. This is all 0, simple 0. Simple 0 with no exponent. Exponent is equal to 1. 0, simple 0 with exponent equal to n. Let's now have a ball. It's the opposite case. We're going to find that we have really the opposite case of that. Number 6. Simple ball. And we're going to do directly the one with exponent. So h of omega equal to 1 divided by 1 plus j omega divided by omega c to the power of n. Okay, so we can simplify that. So h of omega equal to 1 plus j omega divided by omega c to the power of minus n. So 20 log 1 the 1 plus j omega divided by omega c to the power of n. So that will lead us to 20 minus n minus 20n log 1 plus j omega divided by omega. Again, we have two cases exactly the same. It would be exactly the same as this one. Look, here we have 20n log 1 plus j omega over omega c minus 20n. So everything will be the opposite. I'm going to show you now. So omega divided by omega c much less than 1. In that case, it will be minus 20n log 1 minus 20n log 1. We're going to neglect the g omega over omega c because it's much less than 1. Okay, so that will be 2 omega divided by omega c. One may say, hey, 1 plus j1 is not 1. Remember, we are doing the magnitudes. That's actually minus 20n, and the magnitude, that complex number is 1 squared plus omega divided by omega c squared. So 1 plus divided by omega c squared is much less than 1. So we're going to neglect it. Okay, that's why we end up approximating that into that. Okay. Yes, we can't, of course, say that 1 plus j something is approximately equal to 1. No, the magnitude of that. So omega divided by omega c much larger than 1. This is the second case. That case here, we're going to now neglect the 1 compared to omega over omega c. So this would be minus 20 n log omega divided by omega c. Again, we take some values for that. Omega equal to omega c. This will give us minus 20n. Look, it was how much? It was 20n. I'm sorry, it was, this would be 0. Yeah, 20 minus 20n log 0, log 1. Log 1 is 0, so this will be 0. So still 0. Omega equal to 10 omega c minus 20n log 10. Log 10 is 1, so this is minus 20n. Omega equal to 100 omega c. That's minus 20n log 100. Log 100 is 2, so this is minus 40n. That's exactly this case here, but just opposite side. Okay, so instead of going up, we'll be going down. Let's do that. Let's do that. So I have like that color here. The y scale is linear scale, so this is 0 dB, but 20 n dB, 40 n dB, and maybe 60 n minus 40 minus 20 n decibels minus 40 n decibels minus 60 n decibels. Let's have here 0.01 WC, 0.1 WC, WC, 10 WC, 100 WC, 1000 WC, and so on. This is omega. Okay. Now let's put the points. So for any value less than omega c, we use to put 0. All these values are 0. And why we continue until even omega c? Because we know at omega equal to omega c, we have 0. Omega equal to 10 omega c, we have minus 20, not 20, minus 20. 100 minus 40. 1000 minus 60, and so on. So we connect these points together. What is that? That's exactly equal to this one, but in the opposite direction. Okay, guys, that's basically the symbol zero and the symbol n. The next video, we're gonna see like real examples of h of omega. There is no omega c there, there is no n there, okay? But we're gonna try to put that h of omega in terms of one of these shapes so that we can draw like the Bode plots. Thank you very much for watching and see you on another video. Bye bye.